Hello! In this video, we are going to prove the following theorem. Suppose xn, yn, and zn are sequences of real numbers such that 1, xn and zn are convergent, where the limit of xn is equal to the limit of zn. And 2, xn is less than or equal to yn is less than or equal to zn for all positive integers n. Then, yn is also convergent, and the limit of xn is equal to the limit of yn is equal to the limit of zn. Now, before we get into the proof, let's first remind ourselves what these three things refer to. Well, by definition of the limit of a sequence, to say that xn converges to x means that for every epsilon greater than 0, there exists a positive integer k, such that for all positive integers n greater than or equal to k, the absolute value of xn minus x is less than epsilon. To say that yn converges to y means the same thing as this, it's just instead we have yn and y. And to say that zn converges to z means the same thing as this, it's just instead we have zn and z. Now, in general, given any two real numbers, a and c, to say that the absolute value of a is less than c is equivalent to saying that the negative of c is less than a, which is less than c. So we're going to rewrite each of these three things as the negative of epsilon is less than xn minus x is less than epsilon. The negative of epsilon is less than yn minus y is less than epsilon. And the negative of epsilon is less than zn minus z, which is less than epsilon. Right, so each of these three things mean the same thing as what we had before. Okay, so now let's get into proving this theorem. Now to start, we are given xn and zn converge to the same value. So let's call that value w. Right, so we have that xn converges to w and zn converges to w. So I'm just going to replace x and z with w. And to prove this theorem, our whole goal is to prove that yn converges to the same value that xn and zn converge to. So we want to prove that yn also converges to w. So let me just replace y with w. And to prove that yn converges to w, all we got to do is prove that this second statement is true. So since we're trying to prove a statement about every epsilon greater than 0, give me an arbitrary epsilon greater than 0. And with this arbitrary epsilon greater than 0, we want to find a positive integer, which makes this statement turn out true. Now, we're given xn converges to w and zn converges to w, which means we know that the first statement and the third statement that we have here are true. Now, since the first statement is true, we know that this first statement works for every positive real number. So it must work for the positive real number epsilon that we have in our proof. So taking epsilon to be the epsilon we have in our proof, we had that there is some positive integer, I'll call k1, such that for all positive integers n greater than or equal to k1, the negative of epsilon is less than xn minus w, which is less than epsilon. And similarly, since this third statement is true, we know that this third statement works for every positive real number. So it must work for the positive real number epsilon that we have in our proof. So taking epsilon to be the epsilon we have in our proof, we have that there is some positive integer, I'll call k2, such that for all positive integers n greater than or equal to k2, the negative epsilon is less than zn minus w, which is less than epsilon. Now remember, our whole goal with this arbitrary epsilon greater than 0 is to find a positive integer which makes this statement turn out true. Well, we're going to take this positive integer to be the bigger of k1 and k2. And with this choice of k, we proceed to show that this statement is true. So we're trying to show for all positive integers n greater than or equal to k, the negative of epsilon is less than yn minus w, which is less than epsilon. So since we're trying to prove a statement about every positive integer greater than or equal to k, give me an arbitrary positive integer greater than or equal to k. I'll call it n. And from here, we want to show that the negative of epsilon is less than yn minus w, which is less than epsilon. Now to start, we know that k is the bigger of k1 and k2, which means that k is greater than or equal to k1 and k is greater than or equal to k2. Well, since n is greater than or equal to k, this tells us that n is greater than or equal to k1 and n is greater than or equal to k2. But remember, we know that this statement is true, which means this statement works for every positive integer greater than or equal to k1. So it must be true for the positive integer n that we have here. So taking n to be the n we have here, we have that the negative epsilon is less than xn minus w, which is less than epsilon. So the negative epsilon is less than xn minus w. Also, we know that this statement is true, which means this holds for every positive integer greater than or equal to k2. So it must hold for the positive integer n that we have here. So taking n to be the n we have here, we have that the negative epsilon is less than zn minus w, which is less than epsilon. So zn minus w is less than epsilon. But remember, we know that this statement is true, which means this holds for every positive integer. Well, so it must hold for our positive integer n. So taking n to be the n we have here, we have that xn is less than or equal to yn is less than or equal to zn. And because this inequality is true, we can subtract w on all three sides, and we get that xn minus w is less than or equal to yn minus w is less than or equal to zn minus w. And now putting this all together, we see that the negative of epsilon is less than xn minus w, which is less than or equal to yn minus w, which is less than or equal to zn minus w, which is less than epsilon. So we see that the negative of epsilon is less than yn minus w, which is less than epsilon. And that is exactly what we wanted to show. And so putting this together, we see that under the assumption n is greater than or equal to k, it follows that the negative epsilon is less than yn minus w, which is less than epsilon. Since n was arbitrary, this means we have shown for all positive integers n greater than or equal to k, the negative epsilon is less than yn minus w, which is less than epsilon. So we have found a positive integer, which makes this statement turn out true. So this statement is true. And we proved this statement under the assumption of some arbitrary epsilon greater than 0. Since epsilon was arbitrary, this means we have shown for all epsilon greater than 0, this is true. So we've proven this entire statement, which amounts to proving that yn converges to w. Since w is equal to the limit of xn and the limit of zn, this means we have shown the limit of xn is equal to the limit of yn, which is equal to the limit of zn. And that is exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.